With this video, we shall demonstrate how to design the Simulink scheme for the PID controller, which is the essential component in all three control schemes: in single loop control, in feed-forward compensation, and in cascade control. After the MATLAB was opened, we must open Simulink. There are two possibilities. We can click this icon, or we can write the command Simulink. We must wait a little bit. Now the Simulink window was opened. I can close this window and try another possibility to click this icon. So we obtained this window. This is Simulink library window, and we must find from different libraries the appropriate components. But let's start with our problem. This is the transfer function of the PID controller. This is the proportional gain and three terms actually: proportional term, integral term, and derivative term. This is the integral time constant and derivative time constant. And this is the well-known response of the PID controller to the step input signal. So we have actually the proportional part in the response, the integral part, and the derivative part, and this red curve is the sum of all three parts. What we shall need to draw this scheme? We shall need two transfer functions for the realization of integral part and derivative part. Then we shall need gain. We shall also need the summer to sum these three parts. Beside these components, we shall also need a component which will realize the input signal, and we shall need a component which will realize the presentation of simulation results. Now I have to open the new Simulink model. I can open clicking with this icon. Here I can open the existing model, but it would also be possible to open the models in this main MATLAB menu. So I will press this icon, and this is the window in which we shall draw the model of the PID controller. The name of this model is untitled. Of course, we have to save this model and to define appropriate name. Let's start to find some components which we need for our PID controller. We can find several components in the continuous library. Of course, we can also use commonly used blocks. In this library, there are very general blocks which are used in many simulation schemes. But I shall go in the specific library continuous. So these are the components. You can see that we can also find the complete PID controller, but it is sometimes difficult to work with such blocks because actually we do not know exactly how they are programmed. So it's sometimes better if one can draw his own realization. What we need is the transfer function. This is the transfer function in polynomial form, and this is what we can find in this library. Then we can go in the math operations library. What we can find the summer, which will be needed, We can also find the gain here. Then we shall go into the sources. We shall use the constant as the input signal with which we shall test this block. And in the library sinks, we can find the scope block, which is usually used to present simulation results. Now I have all components which are needed to draw the simulation scheme of the PID controller. As I have two parts, I actually need two transfer functions, and so I will select this component. I will press the Ctrl and multiply with this block. So I have two transfer functions for two controller terms, and this gain will be used for the controller gain. So the input signal will be connected to the gain, and the results of all three terms will be summed on the summer. But as we need three inputs, we click this block and add here one plus sign. So now I have three inputs. The first connection is this one, the second connection, and the third connection goes from the PID controller. We must also connect this point and this point, and now we must redraw a little bit these components in order to obtain a visible scheme. And so the results will be put to the scope block. The structure of this scheme is actually what is needed to realize this transfer function. But now we have actually all blocks. We must define the parameters of this block. In this gain, I will define the constant Kp. Then this is the transfer function for this integral part. That means the numerator is 1, but the denominator has actually two terms. One is Ti and another is 0. When I say OK, I also see the result, and it is OK because I can see that this is integral part of the controller, which is this part. Now, to define the derivative part, the numerator has in this case two terms. The first is Td and 1, and the denominator has again two terms, 0.1 multiplied by Td and 1. So I notice that I realize this part, this time constant, is actually selected to the fixed value 0.1 Td. If I want to change the color of some blocks, I select these blocks, then right-click, Format, Background Color, for example, Custom, and I will select a custom color. So with this color, I will mark the blocks which represent the PID controller. Before the simulation, let's check again our scheme. This is the gain KP. This is okay. This is the transfer function of this E term of the controller. This is the transfer function of derivative part, but we can find here a mistake. TDS plus 1. It should be 0, so we must correct this part and define here 0. Okay, so this is correct, and this is the sum of all three parts. Now I must specify the parameters of the PID controller, KP, TI, and TD. I can write these expressions in the MATLAB command window, and I will take the parameters which will later be obtained with the computer optimization. For KP, I will select the value 3.6. For TI, I will select the value 23. And for TD, I will select the value 6.6. So the controller is defined. Before we shall start the simulation, we shall also save this model. I click this icon and I will select the name. For example, PID test is the name of this file, and I save this file. And so now everything is prepared to start the simulation. Of course, I can settle many parameters in the simulation configuration menu, but the most important parameter is to settle the simulation time. And this can be done with the value in this window. So I select the number 50. This means the simulation for our specific example means 50 minutes. Now I can start the simulation with this icon. The simulation has just finished. I will open this scope block and I will press this auto scale icon. And so this is the result. This is the response of the PID controller to the step input signal. And we can see that it is what we expected. And according to these expressions here, we could also calculate these specific values of this response.